By the end of this year, a computer that doesn't exist in any normal sense is going to do something no supercomputer on Earth can do, and IBM says they can prove it, not simulate it, not approximate it. Prove it in a way that any skeptic, any rival company, any physicist with a grudge against hype can check for themselves. That is the promise sitting at the center of IBM's quantum roadmap right now, and if it holds up, it will mark the moment quantum computing stops being a laboratory curiosity and starts being a tool. To understand why this moment matters, you have to understand just how many false starts came before it, and just how carefully IBM has built the case that this time is different. For decades, the phrase quantum advantage has been thrown around so loosely that it lost most of its meaning. Researchers would run an experiment, claim their quantum machine beat the best classical computer, and then, months later, someone would find a smarter classical algorithm that matched or beat the quantum result anyway. It happened again and again. Google claimed it in 2019. Critics picked it apart within weeks. Chinese researchers claimed it with photonic computers. The classical community eventually caught up there too. The pattern became almost a running joke in the field. Quantum advantage was less a finish line and more a mirage that kept moving every time someone got close. IBM knows this history better than almost anyone because IBM has been building quantum hardware since before it was fashionable. And instead of trying to win the hype cycle with one flashy headline, the company has spent the last several years doing something quieter and frankly more interesting. It has been building the actual machinery, both the chips and the verification systems, to make a quantum advantage claim that cannot be waved away. That effort came into full view at IBM's annual Quantum Developer Conference in November of last year, where the company unveiled the most significant set of hardware and software advances in its quantum program's history. At the center of that announcement was a new processor called Nighthawk, and it is worth slowing down here, because the design choices behind this chip tell you almost everything about how seriously IBM is treating this moment. Nighthawk carries 120 qubits, which on its own does not sound like a leap forward. IBM has already built processors with hundreds, even over 1,000 qubits. Osprey hit 433. Condor broke past 100. If this were only a numbers game, Nighthawk would look like a step backward. But raw qubit count was never the real bottleneck. The real bottleneck was connectivity, the ability of qubits to talk to each other cleanly enough, and for long enough, to run genuinely complex circuits without the whole calculation collapsing into noise. That is where Nighthawk actually breaks new ground. It connects its 120 qubits using 218 tunable couplers, a 20% increase in connectivity over IBM's previous flagship chip, Heron. That extra connectivity translates directly into circuit complexity, the number of quantum operations the chip can chain together before errors overwhelm the result. Nighthawk can run circuits with roughly 30% more complexity than Heron could manage, supporting up to 5,002 qubit gates in a single calculation. IBM has already mapped out where this goes next. Future versions of Nighthawk are expected to handle 7,500 gates by the end of this year and 10,000 gates in 2027. By 2028, systems built around Nighthawk's architecture could support 15,000 2-qubit gates, spread across 1,000 or more connected qubits linked by long-range couplers. Numbers like that can start to blur together, so here is the plain version. Every additional gate a quantum processor can run before its signal drowns in noise is another rung on the ladder toward doing something a classical computer genuinely cannot follow. For years, that ladder was short. Real quantum computers could run a few hundred gates before decoherence. The slow leakage of quantum information into the environment wiped out the calculation. Getting to thousands of gates reliably is the difference between a demonstration and a tool. But a more powerful chip is only half of the story IBM is telling this year, and arguably the less dramatic half. The second half is about trust, about closing the exact loophole that killed every previous quantum advantage claim. That is where a second processor comes in, one with a stranger name and a much stranger job. It is called Loon, and its entire purpose is not to be fast. It is to be honest. Loon is best understood as a proof of concept, a test chip built to demonstrate every hardware ingredient IBM believes it needs for fault-tolerant quantum computing, the holy grail where a quantum computer can correct its own errors faster than they pile up. To do that, Loon introduces a new kind of long-range wiring on the chip called C-couplers, which let qubits that are not physically next to each other still interact directly. Ordinary quantum chips only let neighboring qubits talk, which forces engineers into painful workarounds when a calculation needs qubits on opposite sides of the chip to interact. Loon's long-range couplers give it 6-way connectivity between qubits, doubling what Nighthawk itself can do, and that 6-way connectivity is not a luxury. It is a requirement for a specific class of error-correcting codes called quantum low-density parity check codes, or qLDPC codes for short, which IBM sees as the mathematical backbone of any future fault-tolerant machine. Here is why that matters so much. Every qubit in existence today is fragile. It loses its quantum state through the slightest vibration, the faintest stray photon, the tiniest temperature fluctuation. Left alone, a single physical qubit is basically useless for any serious calculation because it will decay into garbage before the computation finishes. The entire premise of fault-tolerant quantum computing is that you take many noisy physical qubits and use them to encode one much more reliable logical qubit, spreading the information out so that no single failure can corrupt the whole thing. Doing that requires an error-correcting code, and running that code requires exactly the kind of dense, long-range qubit connectivity that Loon was built to demonstrate. IBM has already shown it can build all the individual pieces. Six-way connectivity, longer physical couplers between distant qubits, additional routing layers etched into the chip's surface, and fast reset gadgets that snap a qubit back to its ground state so it can be reused immediately. Alongside Loon, IBM introduced something just as important as the chip itself, a real-time error decoder, a piece of classical hardware that watches a quantum computation as it happens and corrects mistakes on the fly, fast enough to keep up with the machine rather than analyzing the errors after the fact. Put those two things together, Loon's connectivity and the real-time decoder. And IBM says it has now demonstrated the cornerstones needed to scale these error-correcting codes on high-speed, high-fidelity superconducting qubits. Not the finished machine. The cornerstones. The pieces are on the table, tested individually, and IBM's next job is assembling them into something bigger. That something bigger already has a name, and it is scheduled for this very year. It is called Kookaburra, and it represents a genuinely different kind of ambition than either Nighthawk or Loon. Where Nighthawk chases raw computational power, and Loon proves out error correction hardware, Kookaburra is designed to be the first quantum processor module that can actually store information, not just process it. IBM describes it as combining a logical processing unit with a quantum memory inside a single module using the qLDPC codes that Loon was built to validate. If Nighthawk is the engine and Loon is the seatbelt, Kookaburra is the beginning of an actual vehicle, something that can hold a computation, not just perform one. And Kookaburra is not meant to work alone. IBM's roadmap describes linking 3 separate Kookaburra processors together through chip-to-chip couplers and communication links, forming a combined system of more than 4,000 qubits. That is the point where quantum computing stops being about a single chip in a single cryostat and starts becoming what IBM calls quantum-centric supercomputing, a genuinely modular architecture where multiple quantum processors, plus the classical computers needed to control and read them, work together as one coordinated system. It is a strange, almost architectural way to think about computing, more like a data center than a single processor, and it is exactly the kind of infrastructure that would be required if quantum computing is ever going to graduate from research tool to industrial workhorse. All of this hardware ambition would mean very little without a way to prove any of it actually works, and this is where IBM's most underrated move of the year comes in. Rather than announcing a quantum advantage claim on its own terms and daring the world to disprove it, the way every previous claim in this field has played out, IBM instead built the disproving mechanism first and handed it to outsiders. It is called the Quantum Advantage Tracker, and it is exactly what it sounds like. An open community-run system for monitoring and verifying claims of quantum advantage as they emerge, rather than after the fact. IBM did not build this tracker alone. It partnered with the quantum software company Algorithmic Keys with researchers at the Flatiron Institute and with the quantum benchmarking firm Blue Qubit, specifically so that the people checking IBM's homework would not be IBM itself. The tracker currently supports 3 categories of experiments where a quantum advantage claim could plausibly be tested and verified by the wider community. The first is observable estimation, essentially calculating a specific measurable property of a quantum system with a precision that classical simulation cannot match. The second is variational problems, the kind of optimization tasks that show up constantly in chemistry, materials, science, and machine learning, where a quantum computer searches for the best possible answer among an enormous space of possibilities. The third is classically verifiable problems, calculations structured so that even though a classical computer cannot solve them efficiently, it can still check whether a proposed quantum answer is correct, which is precisely the property that lets outsiders catch a false claim. One of the earliest contributions to that tracker gives a preview of what these results actually look like in practice, and it is worth walking through because it shows the difference between hype and verification in concrete terms. Algorithmic Q designed a model deliberately built to sit in a regime so computationally messy that every state-of-the-art classical method tested against it has failed to keep up. Researchers at the Flatiron Institute then ran independent simulations, attempting to replicate the result using classical supercomputers, and confirmed that the problem really does appear to be classically hard. Not just difficult, but hard in the specific mathematical sense that matters for a genuine advantage claim. That is, the entire model IBM is now applying at scale. Make a claim, publish the data, invite the best classical computing minds in the world to try to break it, and only count the win if they fail. This approach is also why IBM has been unusually candid about what still has to happen before any of this becomes final. Company researchers have been explicit that verified advantage is still a high bar, and that the best classical algorithms in the world keep improving too, which means the target IBM is chasing is not standing still. Every time quantum hardware gets better, classical algorithm designers get a little more motivated and a little more clever in their attempts to catch up. That tension is not a flaw in IBM's plan. It is the entire point of building an open tracker in the first place, because a quantum advantage claim that survives serious, sustained pressure from the classical computing community is worth infinitely more than one that simply goes unchallenged. There's a quieter piece of this story that gets far less attention than the chips themselves, but arguably matters just as much for whether any of this scales, and that is where these processors are actually built. For years, IBM manufactured its quantum chips using fabrication techniques adapted from older generations of classical chip making. This year, the company shifted quantum chip production to an advanced facility using 300mm wafers, the same scale of semiconductor manufacturing used for cutting-edge classical processors, at IBM's Albany Nanotech complex in New York. That might sound like a manufacturing footnote, but it is closer to a structural change in how fast this entire field can move. Larger wafers mean more chips per production run, tighter and more consistent fabrication tolerances, and dramatically faster iteration between one processor design and the next. IBM says this shift alone has already cut the time required to build each new generation of processor by at least half, while allowing multiple chip designs to be researched in parallel instead of one at a time. In an industry where processor generations used to take years to move from concept to working hardware, that kind of manufacturing leverage compounds quickly. The software stack running on top of all this hardware has been evolving just as fast. And it deserves its own mention, because a faster chip is worthless without the tools to actually program it efficiently. IBM's quantum software platform, called Qiskit, received a significant round of upgrades alongside Nighthawk and Loon. New dynamic circuit capabilities improve calculation accuracy by 24% at scales of 100 qubits or more, a meaningful jump for exactly the kind of large, complex circuits Nighthawk is now capable of running. Perhaps even more consequential, new error mitigation tools that lean on high-performance classical computing alongside the quantum hardware have reduced the computational cost of getting accurate results by more than 100 times. That number is easy to skim past, but it represents something important. It means researchers can now extract trustworthy answers from noisy, real-world quantum hardware using a small fraction of the classical computing resources that used to be required, which makes running serious quantum experiments dramatically more practical for labs and companies that are not IBM itself. Put all of these threads together, the Nighthawk processor with its expanding gate capacity, the Loon chip proving out the connectivity and decoding needed for error correction, Kookaburra bringing memory and modularity into the picture, the quantum advantage tracker turning claims into testable, falsifiable science, the shift to advanced wafer fabrication accelerating how fast new chips can be built, and the software improvements making the whole system more efficient to actually use. And you start to see why IBM's Director of Research, Jay Gambetta, has described this moment the way he has. There are many pillars, he has said, to bring truly useful quantum computing to the world. That word pillars is doing real work in that sentence. It is not one breakthrough carrying the entire weight of the announcement. It is an entire structure, built deliberately, piece by piece, so that no single failure point can bring the whole thing down. That structural thinking is also, frankly, IBM playing the long game against its own history of overpromising. This is a company that has watched its own hardware milestones get announced with enormous fanfare, only to fade into the background once the practical challenges became clear. Osprey's 433 qubits, when it launched, represented a computational space so large that the number of classical bits needed to represent a single quantum state on that chip exceeded the total number of atoms in the observable universe. It was an almost unbelievable statistic, and yet raw qubit count alone never delivered a verified quantum advantage, because scale without connectivity, without error correction, and without a rigorous way to check the results is just complexity for its own sake. IBM appears to have absorbed that lesson completely. Nothing about Nighthawk, Loon, or Kookaburra is chasing a headline number. Every design choice traces back to the same underlying question. Not how big can this get, but how do we prove beyond reasonable doubt that this machine did something no other machine on Earth could do? So what does the rest of this year actually look like if IBM's roadmap holds? Nighthawk continues to scale toward its 7,500 gate target, run through both cloud access and on-site systems for the researchers, and companies already using IBM's quantum hardware. Loon's real-time decoder gets tested against increasingly complex error correction scenarios, building toward the moment when a logical qubit built from many physical qubits on Loon, or one of its direct successors, demonstrably has a lower error rate than any single physical qubit could achieve alone. That specific demonstration, a logical qubit definitively outperforming a physical one, is one of the most anticipated milestones in the entire field because it would be the first hard proof that error correction is working the way the underlying theory has always promised it should. Kookaburra moves from a roadmap entry into an actual assembled prototype, testing whether a logical processing unit and a quantum memory can genuinely function together inside one module. And the Quantum Advantage Tracker keeps accumulating results, inviting more challenges, more independent classical simulations, more attempts by outside researchers to prove that a given quantum result was not actually as hard as it looked. It helps at this point to step back and ask a more basic question, one that often gets skipped in coverage of quantum computing entirely. Why does any of this matter outside a physics lab? The honest answer is that certain problems scale so explosively with size that classical computers, no matter how large or how fast, simply run out of road. Simulating the behavior of a moderately complex molecule, the kind pharmaceutical researchers need to understand to design a new drug, requires tracking an amount of quantum information that grows exponentially with every additional atom involved. A classical supercomputer can approximate small molecules reasonably well, but for anything resembling a real drug candidate, or a new battery material, or a novel catalyst, the exact quantum behavior quickly becomes impossible to compute directly, no matter how many racks of classical hardware you throw at it. A quantum computer, because it is itself governed by the same quantum mechanics as the molecule it is simulating, does not face that same exponential wall. That is the entire theoretical case for why this technology could eventually reshape chemistry, material science, logistics, and cryptography. And it is also exactly why a verified, undeniable demonstration of quantum advantage matters so much. It would be the first hard evidence that this theoretical promise actually translates into a working machine, rather than remaining an elegant idea confined to textbooks and simulations. It is also worth acknowledging that IBM is not chasing this milestone in isolation. Google, several well-funded startups, and research groups in China have all pursued their own versions of a quantum advantage claim over the past several years, each with different qubit technologies and different definitions of what counts as a win. That competitive pressure is part of why IBM's emphasis on open adversarial verification stands out as a genuinely different strategy rather than just careful marketing language. In a field crowded with competing claims, being first to announce a result has repeatedly proven far less valuable than being first to announce a result that nobody can subsequently tear apart. IBM appears to be betting its entire roadmap on that distinction, wagering that durability, not speed, is what will ultimately define who actually gets remembered as having crossed this line first. Behind all of this sits a longer horizon that IBM has been remarkably specific about, given how unpredictable this field has historically been. The company is committed to large-scale, fault-tolerant quantum computing by 2029, built around a system named Starling, planned for construction at IBM's site in Poughkeepsie, New York. The roadmap towards Starling runs directly through everything happening this year. Loon proves the hardware components. Kookaburra proves the modular assembly. A processor codenamed Cockatoo, slated for 2027, is meant to demonstrate entanglement between separate modules using what IBM calls a universal adapter, effectively teaching multiple quantum processors to function as extensions of a single machine rather than isolated devices. By 2028, IBM expects Starling to demonstrate something called magic state injection across multiple modules, a specific technique required for certain advanced quantum operations that cannot be performed through error correction alone. And by 2029, the plan calls for Starling to scale into a system capable of running 100 million gates across 200 logical qubits, a scope of computation that would have sounded like science fiction even 5 years ago. It is worth pausing on just how audacious that final target actually is. 200 logical qubits does not sound like much next to the 1,000+ physical qubits IBM has already built into processors like Condor. But a logical qubit, remember, is built from many physical qubits working together, specifically, so that errors cancel out instead of accumulating. 200 reliable, error-corrected logical qubits, capable of running 100 million sequential operations without the calculation collapsing into noise, would represent a fundamentally different category of machine than anything that exists today. One capable of tackling problems in drug discovery, material science, cryptography, and optimization that remain completely out of reach for classical supercomputers, no matter how large those supercomputers get. None of this is guaranteed, and IBM has been careful, publicly, not to pretend otherwise. Independent voices covering this field have pointed out that verified advantage remains a genuinely high bar, one that has claimed the credibility of nearly every group that has attempted to clear it before now. The best classical algorithms keep getting sharper, sometimes uncomfortably close on the heels of quantum claims that once looked untouchable. Fault tolerance by 2029 assumes that every intermediate milestone between now and then lands roughly on schedule across hardware, software, fabrication, and verification simultaneously, which is an enormous number of moving parts to keep synchronized over multiple years. But what makes this particular moment in IBM's roadmap different from the false alarms that came before it is not certainty. It is structure. Every claim comes with a mechanism built specifically to test and potentially break that claim. Every chip released this year has a clearly defined job inside a larger architecture, rather than existing as a standalone headline. And every date on the roadmap, 2026 for advantage, 2029 for fault tolerance, comes attached to a specific falsifiable technical milestone that either happens or does not. That is ultimately what makes this story worth paying attention to right now, in real time, rather than waiting to read about it after the fact. Quantum computing has spent the better part of 2 decades living in the gap between theoretical promise and demonstrated proof, a gap filled by equal parts genuine progress and genuine hype, often tangled together so thoroughly that outsiders could not easily tell which was which. IBM's current roadmap is, in essence, an attempt to close that gap using the most boring, most reliable tool available, open verification. Not a bigger announcement, not a flashier qubit count, a tracker anyone can inspect, a set of experiments anyone can attempt to break, and a chip-by-chip build toward fault tolerance where every single piece has to earn its place before the next one gets added. By the end of this year, according to that roadmap, the world should know whether a quantum computer has finally done something classical computers genuinely cannot do, checked not by IBM's own marketing team, but by an open community built specifically to catch exactly that kind of overreach. If it happens, it will not arrive as one dramatic headline. It will arrive as one more entry on a public tracker, quietly outlasting every attempt to disprove it, which, after decades of quantum advantage, claims that collapsed the moment anyone looked closely, might be the single most convincing thing about it, and that, in the end, is the real story hiding underneath all the qubit counts and coupler diagrams. It is not really a story about one chip, or one company, or even one year. It is a story about a field finally growing up, trading spectacle for scrutiny, and betting that the slower, harder path of open verification is the only one that actually leads somewhere permanent. Whether Nighthawk, Loon, and Kookaburra deliver on that bet by the end of this year remains to be seen, but for the first time in a long time, the mechanism for finding out is already sitting in plain sight, running in public, waiting for anyone willing to look.